Let's now talk about iterators. In the previous lecture, we learned about an abstraction called list. This is a sequence where the order of elements matters. And in this abstraction, nothing was specified about how the underlying data should be stored. As we saw, it could be stored as an array, it could be stored as a linked list, it can also be stored in some other way, not yet known to us, but in the future it could be stored in another data structure. As a matter of fact, if we correctly implement any abstract data type, we should not know or care what the data structure is used underneath. We should not have any access to the underlying data structure. List requires the following operations to be supported by any implementation. Get element by position, search the position of a given element, add new element at a given position, remove element from a specified position. We saw how both array and linked list implementations support all these operations, but with a different degree of efficiency. However, there are some tasks that all these operations might be insufficient, and we might need access to the underlying implementation, to the underlying data structure. Today we will see what can we do in order to avoid access to the underlying data structure. Let's take, for an example, the task of getting the frequency of an item in a list. We want to count how many times a given element O is encountered in a list. Using the operations which are already supported by the list, we can write a loop where we will get an element from every position of the list and compare it to O. If they are equal, we increment the accumulating counter. The question which we need to address is, would this method work equally well for both array list and the linked list implementations? And the answer to this question is no. This method will be really inefficient for the linked list implementation, because each time the get is called, we would need to start traversing the list starting from the head. While for array implementation, this whole loop is a linear time loop, for the linked list, this is a quadratic time loop, because each get needs to start from the beginning, traversal. And we do not want any quadratic time algorithms for such simple task as traversing the list once. Efficient solutions to this problem exist both for an array list and for a linked list, only they are fundamentally different. In both cases, we can traverse the entire collection in linear time. However, in the array list, we use an index to access an element at position I, while in linked list, the entire loop is just following a sequence of links. The principle of encapsulation and the wall between ADT and the inner implementation forbids us access to the head of the linked list. As a matter of fact, the user of our implementation doesn't even need to know that there is a list, linked list behind the scenes, right? It only needs to know that it can get whatever it wants from this sequence. So we are facing the following problem. We want an efficient and uniform dispensing of values from an underlying data structure in such a way that we do not violate the integrity of the abstract type, that we do not allow access to the data structure itself. To do this efficiently, we will conceive a new abstract data type called an iterator, and we will implement the iterator differently for each of the data structures behind our list ADT. So we will extend the operations common to all lists, all these operations. We will extend it with one more new operation, which we will call iterator, which will return this new ADT called iterator, which we will later use for an efficient traversal of the list, no matter how it is implemented. The goal is to be able to ask any list to return an iterator which has inside a data structure specific implementation, and then use this iterator in a very uniform way. We can loop now through the sequence of list values using the following loop. While iterator still has elements, dispense the next element from the underlying sequence. Iterators that we are going to create will provide a functionality for efficient traversing of all the values in the list. We can implement these iterators differently depending on the underlying data structure. We will make each iterator to be able to do the following two operations. The Boolean has next will answer if there are more elements to traverse, and the next will return the next element in sequence. What do we need to know between separate calls to next? We need to maintain the state of the iteration by making the position in the sequence where we currently stand with our iterator. That is in order to not to restart the iteration each time we call next, because for example, for the linked list, it will not end well if we start every time from the beginning. Here is a simple implementation of the iterator for an array list. Note that this iterator class is inside the array list class. It has access to the data structure, to the array, which is inside the array list class. Inside the array list iterator, we have a reference to the actual array list. This reference is set up in the constructor of the array list iterator. So this iterator has connection to the list from which it is created. The variable index of next stores the current state of the iteration, the position in the array to be returned next. The hasNext checks that the index of next is within the valid bounds. It points to a valid array element. And if this is true, if hasNext returned true, then we can request the element at the position index of next. And we will return this element when somebody calls next. At the same time, we advance the index of next to point to the next position in the array. The method iterator inside the array list will return a new instance of this particular array list iterator and pass to it as a parameter the array list itself. Let's now see how should we implement the iterator for a linked list. As before, we have a reference to the actual linked list inside which the iterator class resides, and this reference is set up during the construction of the iterator in the constructor. The state of iteration is stored in a different variable of type node. When we initialize our iterator, we set the next node to point to the head of the list. Recall that we want to use this iterator in the following way. We want to loop over the underlying elements, and we want to ask if there are still elements to visit. Return the current element and advance to the next element. So if you understood what we want from our next and get next to do, try to select the correct implementation in top hat. First, try to select that for the next. And now select the correct implementation for the hasNext. Putting it all together, we get the following linked list iterator, where hasNext basically answers, can we still call next? Does the next node still point to the valid node with data. And then in the next, we store this data in a temporary result and then advance the node to the next node in sequence. Then we return the result. So after we implemented the linked list iterator, we can, in the iterator method of the linked list, ask to return an instance of this iterator by initializing its connection to the current list in the constructor. So finally, we have a uniform traversal using the iterator. See? So we will ask for any list to return the iterator, the list-specific iterator, the iterator which has access to the underlying data structure. But after that, we are doing everything very uniformly in the same exact way. So to summarize our lesson about iterators, iterator objects provide a unified interface for traversing a list abstract data type. They have access to internal data representations of each list. They are efficient because they store the current state of the traversal and do not need to restart from the beginning. To implement an efficient iterator, you need to understand the mechanics of the underlying data structure and the complexity of its operations.